Hi, welcome. My name is Mustafa Yashinyurt, and I will be presenting for my CS259 Advanced Parallel Processing term project, incorporating parallelism into fully homomorphic encryption schemes. So without further ado, let's get started. So let's start with what is homomorphism exactly? We understand that the key goal in achieving homomorphism is to reduce security risks, specifically on cloud environments. Where homomorphic encryption is very helpful is that it allows us to process encrypted input and send out an encrypted output as a result without decrypting any of the input and revealing any sensitive information, potentially, to any malicious users that may be watching. Now, this is hugely useful in protecting, especially cloud environments. Many commercial or many companies will want to use cloud computing in order to compute their various data. However, those environments are not exactly safe, so they need to find a way to make this to make that unsafe environment in that unsafe environment keep their data safe. And so this is a way of doing just that by using homomorphic encryption schemes. And uh, exactly the logistics of homomorphism can be explained in a couple different analogies. So let's consider the first one. We know, for example, that the basic arithmetic fact of 1 plus 2 equals 3. Well, it just so happens that in encryption schemes, we observe that if we encrypt each individual piece of that equation and sum them together, it's true that the encryption of 1 plus the encryption of 2 equals the encryption of 3. Similarly, we can consider, if we want to have a more literal example, let's consider something with regard to just common characters that we see. For example, if I wanted to spell my initials MY, then we would say, okay, we would just concatenate those two characters together. Similarly, if we concatenated the encryptions, the ciphertext versions of those same characters, we would get the same thing. The operation remains the same and the end result is the same. It's just that the format is a bit different. And sometimes it's dependent on the kind of encryption. And I like the example of the two different zodiac ciphers. First of which was figured out very easily by just a history teacher and his wife way back, like just within a few hours of learning the cipher and it being put out to the public. Whereas the second one took until just this year, 2021, to be broken by some top cryptographers. And so, for example, let's look at the reason being in the first zodiac cipher, you just need to use what the machine learning technique of hidden Markov models. Essentially, it's a way to categorize the ciphertext into different categories. So, for example, if you use only two hidden states, you separate them into vowels and consonants. Essentially, what separates the first two zodiac ciphers is that one is much more recognizably English than the other. And that's what the hidden Markov model picks up on. Not the case with the second one because there's all sorts of diagonal reading and crazy stuff that's totally separate. But really, this follows the principles of homomorphism because we observe that there is a fundamental connection between how we would normally interpret this cipher and how we would normally interpret the message hidden in this cipher and how the cipher itself is constructed. That is the key there. And so we are employing that same key when it comes to arithmetic computations. Specifically, we'll be using additive, or we'll be looking at addition and multiplication operations as subtraction and division, or no, okay, subtraction and division are less frequently used, but not necessarily impossible. Additive homomorphism and multiplicative homomorphism make up the two different types here, and together they create what is considered a fully homomorphic encryption scheme. If it's only partially homomorphic, that means it's capable of only one of those. And we'll see in the next slide here that there are a couple different examples that we can look at in history. Specifically, the RSA algorithm and the El-Gamal algorithm both only, or the RSA algorithm only a couple years coming out after the Diffie-Hellman algorithm, which is the basis of both of these, are both multiplicatively homomorphic, not additively, only multiplicatively, and thus only partially homomorphic. The first fully homomorphic solution is due to Craig Gentry in 2009. And this was published as part of his dissertation. It's filled with extremely taxing computations, so taxing that it can take minutes for just for two 8-bit integers to be multiplied, and hours for two 8-bit integers to do a division between the same integers. Clearly, if we want to employ this commercially or for any company, this is not at all practical. We need to have a better system in play here. We'll see that parallel processing can present a kind of solution to this. And it is a great idea for speed up. We have observed great results in using parallel processing for other tasks throughout history. And we'll see that with with the instructions we have here, that when it comes to addition and multiplication operations, that we open ourselves up to more data hazards by having different roots here, or by having different nodes, different branches. And we can see we follow this tree structure of data dependencies, starting with our very root node. And if you'll notice, each column represents its own, which is its own branch, or node as it's called, represents its own processor as well. So when we see in the figure to the right, we only have 3 branches in this one. And technically, we could, if we were to have any more, yes, we could execute the 4th instruction one step earlier, but we can see via the dependencies, which are exemplified through the arrows pointing upward. Notice that the children nodes point upward, that instructions 6 and 7 have to take place in the 3rd iteration here. So having any number of extra processors really doesn't help this situation at all in this particular example. I like this diagram because it showcases that kind of limiting factor there, that certain instructions are always going to be always going to require other instructions, and there will be this singular chain that will be a preventative kind of, or that will prevent further expansion from happening. In this case, it's instructions 6 and 7. They both require information. They both depend on instruction 5, the b equals c plus c, because both instructions 6 and 7 require b in their operations. And because they both require 5, they have to execute only after 5 executes, which also requires 2. And because 2 is operating in the first iteration, we are stuck with 6 and 7 being forced to execute no earlier than the 3rd iteration. And let's continue here. Okay. And we'll also see that the architecture that is used for parallel processing in fully homomorphic encryption schemes is really not unique at all. It is exactly the kind of processing scheme that we see in common cloud computing platforms such as AWS and Google Cloud platforms, among others. It's a typical client-server model with a dispatcher and different computation servers that itself also mirrors hyper-threaded processors in your typical computer, in your typical machine. And we'll see that this is important later on, the idea of a dispatcher communicating with computation servers, and that this very nature will cause some overhead that will be unavoidable. And so continuing into that, we're going to see that the testing that is used, the testing scheme used in parallelizing fully homomorphic encryption, in the example that was given in the paper that I read, only a home cloud setup was used. And that's something I actually want to touch on after we go through the rest of this slide here. Specifically, the test that was done of interest here is that only 20 random integers were generated, and only within a specific range. And the idea here is to compare the time taken to sum all 20 of them. We'll do it sequentially using the Gentry algorithm, and also in parallel. And we'll see how the time changes, the time difference changes. But circling back to the nature of why this was done in a home cloud setup is because, and this is because it's indicative of a problem that is inherent to the fully homomorphic encryption scheme. The people that did this test don't want to use proprietary software like the aforementioned AWS or GCP because those can be very expensive. We'll see that they are priced by like how much, well, not how much work is done in how much time, but rather a product of the two. If you do a lot of work or you spend a lot of time, price required or the price goes up. And so fully homomorphic encryption, especially Gentry's algorithm, suffers from that quite a bit. We see that because it takes so long, it's just not practical to use these cloud computing softwares. And this is because because it's not suited to experimental and research oriented operations to begin with, but in a commercial context, especially if we want to do extensive uh, deployment of this kind of encryption scheme, the bill is going to run up very, very quickly. And very little work will probably be done in that time. I don't see how it can be deployed in a scalable, workable context. So, fully homomorphic encryption, just by looking at the nature of how the cloud setup is impractical and expensive, can already see that that is extremely limiting on what we can really expect from fully homomorphic encryption schemes in the current time, in the present day. And frankly, I don't see that aspect of cloud computing changing anytime soon. It's always going to be a pay per use kind of scheme. And if that is, and so we could expect then that we will see more home cloud setups done in the future, especially with regard to government bodies that will definitely want to be putting FHE into practice. But can we really expect that those will really be effective? Well, that's the point of this test. So for the summation method, it's going to be very similar to what we had seen in the previous diagram. We're just going to split each one pairwise in terms of following the data dependency graph, similar in that sense. We want to split the 20 integers into different pairs, specifically 10 different pairs, and add those pairs separately. So when we generate and add a new integer to add, then we just split those into pairs as well. So we'll go from 20 different integers down to 10 different integers, down to 5 different integers, and then we'll just add the rest from there, 2 and 2, and then the last one. And we think this is simple enough, and it is very simple, and sure enough, it doesn't perform particularly well. The speed up is noticeably lacking. Even when and the test was given for different numbers of branches throughout. Some only had 2 nodes, others had 4 nodes, and eventually went to 8 nodes, and we see that there is a steady increase up until we reach the 8 branches, where there is too much overhead. If we look carefully, and this could probably be mediated if we had been working with a larger number of integers, because the numbers don't really if we think about how there are only 20 integers there, then 8 branches is probably too much. If we are intent on using every single branch involved, then the overhead invoked from switching between them would probably be a little too much with regard to with smaller numbers of branches. And another point that is noted is the nature of the hyper-threading here. So the specific setup for the cloud that was done in this experiment was that it's really just 2 high-powered laptops linked together. And The way they're linked together is that and because we're using just raw machines, these machines here use hyper-threading in their operating systems. And because their processors are split into two different into two different threads, the operating system is tricked into thinking that there are two different uh, concurrently running processes. But of course, only one process can execute at a time. And because there is no way for the user to control where these processes go, how they are hyper-threaded, even if they have an ample number of processors and processing cores in those two machines that they are linking together in a cloud server, doesn't mean that they're going to be executed really simultaneously. So we run into essentially a problem uh, in how the cloud itself is kind of set up in that regard. And may also be the case for cloud instances or instances on cloud platforms like GCP and AWS. Uh, we don't really know that for certain, but it's something that can be expected going forward. And so clearly, this is just indicative of a larger problem that if we had such little speed up, it's not necessarily the problem with the cloud computing style itself. Rather, the algorithms behind that need to change. We need to do more research into figuring out exactly how we can improve these algorithms. Gentry's algorithm came out in 2009, so it's been quite a while. It's been quite some time since then. However, not too much progress has been made in getting in speeding up the operations involving encrypted data. And this is problematic because cloud usage is becoming much more popular, especially since 2009. Uh, AWS and GCP and Microsoft Azure and all those other ones, uh, companies are using them more and more. And if companies are relying on them that much more, then they're going to need a way to secure them more properly. Can we rely on those companies to do it themselves? Perhaps, but we don't know for certain. It's better to have a true fail-safe in play before we go about using these um, before we go about using cloud technologies that may be a little uh, maybe a little unsafe. They're not local necessarily to the companies that are using them. And that brings to mind another thing. Cloud usage is really expensive, especially if we're trying to do FHE, fully homomorphic encryption. And it's expensive because the algorithms themselves are not very are not very efficient in terms of time complexity. They perhaps need more optimization. Overall, in that regard, the parallelization element is a little premature because we don't really think that there is any kind of uh, like there is noticeable improvement, but it's not so noticeable that it makes up for the fundamental problems before underlying in FHE. And ultimately, we have quite a ways to go before we think about making fully homomorphic encryption into a household thing, into something that is commonly used, and not just in households, of course, but by tech companies and any kind of company or government around the world. Uh, Here are the sources I used here, the references, and thank you for listening. Right, have a good one.